Okay, so remembering where we left off last time, Mr. Aufbau, Mr. Pauly, and Mr. Hund here. We have to assign residents kind of the way that they're supposed to be set according to those rules. So we'll start on the first floor. Remember, we have to start on the first floor because Mr. Aufbau said we have to start on the ground floor and then work our way up. And then we'll fill in as accordingly. So according to Mr. Pauly, he also says that we have to fill in the top bunk first. So we'll represent that with our little arrow. And then a down bunk. So our bottom bunk. So then top, then bottom. Second floor, because we're not going to go to the third floor. Fourth floor, because again, Mr. Aufbau says we start from the bottom. And then we go our S to start off with. So we're going to fill in our top bunk. Now, which one of these next rooms are we going to do? You're going to do the P's, going to go to the, going to do the bottom bunk here. Well, it turns out you're going to go ahead and pair this guy up because according to Mr. Hund, he says that you cannot cannot put electrons in any in the same box if or unless all the other boxes of the same type also have at least one. Now, since there's only one of the S types, once you have the top bunk, well, you have no choice but to put in the bottom bunk. Now, move on to the P's. So this is where the pattern of how you fill becomes important. So with P again, we'll start off here in the first room. We'll go with the top bunk. And then our next resident will actually end up getting put in this second one because, again, Mr. Pauly, or Mr. Mr. Hund says that we have to make sure each of these rooms has at least one electron first before we can pair them up. So each of these rooms, again, will have an individual resident. Kind of like, it'd be nice having your own room. If any of you share rooms with anybody at home, you know what that's like. It's nice having the room to yourself. And then we go back and fill in the rest of them. So then we go back and pair them up. So we'll do the down, and then the bottom bunk, right? Then we have our next floor. The third floor is our next one. So we'll do our S like before. So S, so up and then down. We'll do our P, so we'll make it up, and then up, and then up. Then we do our down, and then our down, and then our down. And then we go to the D rooms and essentially do the same thing. So we go up, and then up, and then up, and then up. Oh man, that's getting worse. Okay, and then down, and then down, and then down, and down. Okay, so you get the pattern here. So I don't want to kind of belabor the point, but essentially you get the idea here is that there's a specific pattern in which you fill in these rooms. Now again, these are just little examples here. I'll let you have a second here. I'm going to sort of let you take a moment. You can pause it here, and then you can figure out what the answers are. We'll get the answers up in just a moment. Okay, and here are the answers. The first one, you can see that it's all on the third floor, or the 15th residence on the third floor in the P room. It's a third of the P rooms, by the way. So the one closest to the right. 2, 3, 4, pretty straightforward. 5, again, I'm asking for the total number of electrons it takes to fill up our 2p orbitals. In this case, it'd be the rooms. And then, does a 2f room exist? And the answer is no. You can see on the previous slide, there's no such thing as a 2f. Right? Only 2s and then 2p's, no 2f. Okay. Of course, we're looking at the analogy, so we've got to figure out which of these are. What does each floor represent? Each floor represents something called the energy level. I've mentioned that a couple times. This is the same kind of thing as the n equals 1, n equals 2 thing that we saw earlier with the Bohr model. Then, each resident represents a single electron. Each room represents an orbital, and this one, last one, was supposed to say which does each room type represent, or the SP, the D, and the F rooms, and those represent the type of orbitals. So again, what does each room type represent? That's how it's supposed to read. Represents again each of the types of orbitals. Okay, moving on. This here is a fairly complex looking chart, but in fact isn't so bad. Let me go ahead and break this down for you. Over here on the left side is going to be the energy level. So n equals 1, n equals 2, n equals 3, so on and so forth. And this technically goes on for infinity. What this n again represents is the energy level. Now, within each energy level, notice that you have differing numbers of what things exist. On the n equals 1 level, you only have the s orbitals that exist. It's kind of hard for you to see here, but this is actually a little sphere like we saw earlier on a previous slide. But notice again that there are none of these p orbitals. Right? So this p right here, there's 3 of them, and there's only and none of them are appearing in the first energy level. Same thing with the d orbitals. None of the d orbitals exist in the first energy level, nor the f, and you can probably presume that none of the other types of orbitals that exist exist in the n equals 1. Then, if you look at the n equals 2, you have the s and the p's. At the third energy level, you have the S, and then the P's, and then the D's. And the fourth energy level, you do have an S, a P, a D, and an F. Now, that's again not the biggest deal here. The main thing I want you to pay attention to again is how these are broken down. So if you notice, there's actually within the P's, there's also a lot of symbols here. L equals 1, M equals 0, and so on and so forth. That's not super important. The main thing I want you to get out of this is that there's actually 3 of the p orbitals. Now, this gets a little confusing. The term that we use here is degenerate. Right? This is, again, a set of degenerate 2p orbitals, meaning that these 3 orbitals are essentially of the same energy and are the same type. So this p, z, px, py, these actually reside on 3-dimensional axes. Not important here. But yeah, you have 3 of them. Then you have your d orbitals. Well, the 3 d's again is the first place in which they exist. You see the this one right here is dz squared, dxz, dyz. I'm not concerned about that. The main thing I want you to know again is that there are 5 of these types. Right, so I take that back. There's 5 of this specific type of orbital. In this case, it's the 3d orbitals. And then if you look over here, the f orbitals, again, these are way more complex. I would never ask you to really know what these look like. But again, you see that these have f, z cubed and f xz squared and all of this sort of complex stuff. I'm not too worried about that. The main thing you need to know, again, is that there are 7 of this one type of orbital. Like I said earlier, the one comment I want to make here anyway is that the P's, these are supposed to look like dumbbells. Well, most of the shapes that we show you, at least at a very rudimentary level, is kind of this very simple double-lobed object. The more and more complex it gets, meaning the higher and higher in energy it gets, actually it resembles a dumbbell shape more and more. And this, the bar that goes across, and these are where the majority of the mass would be, so you'd have something you can curl and get your biceps nice and big. But again, the main idea here is that there's a shape that doesn't quite appear on the simplest level, which we show is this. Also, right here, these are actually cross sections of the s orbitals. They really should be spheres, but they're trying to show you the insides. Each of these individual rings is kind of segmented by nodes. Now, I get nodes. Don't worry about that. Just in case if you wanted some context there, that's why. So again, as a review, you have each energy level, n equals 1, 2, 3, 4. You see that each energy level has possible orbital types. In this case, n equals 1 has s, n equals 2 has 2 orbital types, n equals 3 has 3 orbital types, n equals 4 has 4, so on and so forth. And you should know that within each orbital type, you need to know how many orbitals there are, and the term we use again is degenerate orbitals. So in any case, at 5d orbitals, there will always be 5 5d orbitals. Because you see 1, 2, 3, 4, 5. There will always be 5 4d orbitals. There will always be 7 4f orbitals. Alright? Moving on. Just as a visual, this is kind of a representation of what it would look like if all of the orbitals actually existed in one space. So if you can kind of imagine, really this right here is the s orbital. This is a single s orbital. If you were to overlay the p orbitals that also exist, it would kind of look like this. Remember that there's 3 p orbitals, so this is one of them. This is one going that way, and this is our third one going this way. So again, it's kind of like you have the space that sort of occupies each other. If you added the d's in, then it gets a lot more complicated. You notice you see all these little lobes coming out of it. Those each represent a part of an orbital, and then obviously the more and more reality and more realistically, if you included all the orbitals, it would look like just a giant bulbous mess. Now again, this is just a context thing showing you what it looks like if you were to combine them all into one space. Okay, now let's get into the real stuff here. So arrangement of atomic orbitals. Let's go ahead and talk about how this is supposed to be done. Remember that the reality of the Aufbau principle isn't quite as easy or quite as simple as we said earlier. The Aufbau rule actually says the electrons are filled by orbitals in increasing energy, not energy level. Previously, the energy levels was represented by each of the floors of the dorms. In this case, again, each energy level is again sort of representing that, but we're talking about the energies here. So you see this arrow right here is showing the just amount of energy. Don't worry about the values or of units there. I'm just showing you energy. The Pauli exclusion principle says that 2 electrons in an orbital must have opposite spins, meaning the up and then the down spin. So this part was the up and then the down. Before we just get the top bunk and bottom bunk. But in reality, there's something called spin here that must be different in each single orbital. And the last one is Hund's rule. Electrons in degenerate, that word comes back again, orbitals cannot be paired until at least all orbitals have at least one, and the word here now is not energy level, but it should be electron. Again, the word here, degenerate, meaning the orbitals of the same energy. So these right here are a set of degenerate orbitals because, again, they're all in the same energy. Okay. Now let's go and have a little bit of practice here. And let's start off with carbon. We need to assign the elements or electrons in carbon. Notice that my 1s is a little cut off here, so I'm going to rewrite that in on the side, 1s. And essentially all you have to do is fill in the electrons as we saw earlier. Now I'm going to go ahead and do this one at a time. You do the up and then down. You start down here because it's the lowest energy. Then you go the up and then you down here. For carbon, again, you have 6 electrons to assign. I should probably write that up here. So my 6 electrons I need to assign here. I've already assigned 4, and then I'm going to move on to my next one. So it goes up, and then it goes up. All right, now notice again, the reason why I'm starting at the bottom and working my way up is because of the Aufbau principle. This is the lowest energy level one. This is the lowest energy orbital. This is the next lowest, and then this is the next lowest. It doesn't go from 1s, 2s, and then to 3s. It goes 1s, 2s, and then to 2p because it is the next highest in energy. Right? 3s is a little bit higher in energy than 2p. Also notice that the Pauli exclusion principle says I have to have an up and then a down one. Right? They have to be opposite spins, so I can't do an up and then an up, or a down and then a down. The last one is the Hund's rule, especially applies to these. For my degenerate orbitals, I have an up and up instead of an up and then down. And that's because each of these orbitals needs to have their own individual electron before you start pairing them up. Okay, the next one is sulfur. The next example here is sulfur anyway, so it's going to have 16 electrons. I've already applied 6 of them, so let's go and fill in the rest of them. So it's up, excuse me, that's actually a mistake. Let's pretend I didn't make that mistake. Up, up, and then an up. Again, making sure all these have their own first before you pair them up. And then let's go ahead and pair up the rest of them. So down, and then down, and then down. Okay, so that's again a total of 8 electrons that I have assigned. 12 electrons. Wow, 10 electrons that I've assigned. I have 6 more to go. So it goes up, down, and then up, 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 and down. There you go. So those are, again, my 6 electrons that are in the outermost. So again, it goes 1s, 2s, and then the 2p's, the 3s, and then it goes up to my 3p's. Notice again, I'm going to go straight up to the 4s. Now, what's next after sulfur? Well, after sulfur is taken care of, we have iron here. We're going to look at iron again. Has 20, I believe, 6 electrons to assign. Again, remember that the number of electrons in this case for a neutral atom is the same as the number of protons. So how am I going to assign these? Well, again, notice I have these electrons. I have most of these already filled in. So let's go ahead and do a down, and then we'll have our up, oops, not even close, our down, excuse me. And then we go from 3p, normally we'd want to go to 3d, at least intuitiveness-wise, but if you look at this diagram, again, it goes from 3p then to 4s. So that's the next highest in energy. Then after the 4s, you're able to go back to the 3d. 1, 2, 3, 4, 5, and then your last electron there is 6. So if you go through and count all these electrons, there's actually 26 electrons all for iron. Iron again has sort of this interesting pattern where the last electrons actually again kind of go from 3s, 3p, and instead of going straight to 3d like most of us really want to do, it actually goes to 4s because 4s is the next highest in energy, not the 3ds. So this goes 3p, 4s, and then 3ds. Okay, so what exactly does it tell us? Well, we can actually use this information and actually get some more. But one thing I want to check real quick here, you can take a look at this. If you pause it right now, you can pause it and I'll explain in just a moment. Alright, so hopefully you took some time to look at it. Your big error should be right in here. You have degenerate 3p orbitals, 1, 2, and 3. And notice that you have this one specific electron right here, which is not placed in the correct spot. The rule that's violated here is Hund's rule, H-U-N-D, Hund's rule. And it's because the electron here has been assigned to be paired up with an electron, despite there being another orbital that is still unfilled. Okay, moving on. Now, where do we actually get the, where does this go? So if you remember for carbon, right, we had a couple of electrons here. And essentially what we want to do is write in all the electrons and how they're represented. So for this one, actually I'm going to hold off for just a moment and we'll pick up in the next video.